Hello everyone, you're welcome to this channel once again. Today we have another question from the aerodynamics point of reference. Now let's read through the question given today. An experiment is being designed to measure aerodynamic forces on a building. The model is 1 to 100 scale replica of the prototype. The wind velocity on the prototype is 9 meters per second, and the density on the prototype is 1.2 kilogram meter cube. The maximum velocity in the wind tunnel is 90 meters per second. The viscosity of the airflow for the model and the prototype is the same. Now, calculate the density needed in the wind tunnel for the dynamic similarity. What will be the force on the prototype? Now, today we are dealing with a similarity problem for a prototype and model aerodynamic experiment. Now, from this particular question, how do we approach this? First of all, is by using the Reynolds number of the prototype and the model, whereby we juxtapose two of them together, either to find the density of the model or the density of the prototype. But today we are asked to find the density of the model. So first of all, let's pull out all our parameters. First of all, we're told that the scale of the replica of the model to the prototype is 1 to 10. This is given. So the scale is 1 to 100. Then we're given the velocity of the prototype to be 9 meters per second. We're given the density of the prototype to be 1.2 kilogram per meter cube. We're given the velocity of the model to be 90 meters per second. Now, by juxtaposing or comparing the similarity equation of the Reynolds number of both the prototype and the model together, we have this particular equation. So don't let us forget that Reynolds number is the ratio of rho VL over dynamic viscosity, which gives us this particular equation. So our Reynolds number for the prototype equals the Reynolds number for the model, which gives us this particular equation. So therefore, by calculating the density for the model for this particular experiment, we obtain this particular equation, which gives us 12 kilogram per meter cube. Now that we have found the density needed for the model in the wind tunnel using similarity method or aerodynamic juxtaposing method, now the next thing is to calculate the forces on the prototype. Now don't let us forget that the equation for coefficient of drag equals CDP, that is coefficient of drag for prototype, equal coefficient of drag for model, which gives us this particular equation and this. for both prototype and model. Now we are asked to find the forces, that is the drag force on the prototype, which is dP, by using this particular equation given. So therefore, by using dP equals dm, that is the drag force on the model, multiply by the prototype density and the prototype velocity raised to squared over prototype length raised to 2 over the model density, multiply by the velocity of the model, multiply by the length of the model, both raised into square. So that gives us this particular equation. From there, we can slot in all our calculated values and the given parameters. So therefore, the drag force acting on the prototype equals 10 multiplied by the drag force on the model. So therefore, our dP equals 10 times dm calculated. Thank you very much.